Hi friends, today I'm going to start Math Question Bank 4. So again here I'm going to discuss 10 questions and then I'm going to provide you the solutions. Now through these questions I'm going to introduce some important concepts also, for example the Laplace transform and questions on arithmetic and geometric progression which are often asked by people. Now, this question bank is useful for teachers, professors, research managers, and people who are interviewing STEM graduates, that is science, technology, engineering, and math graduates, because people need to know a basic level of math if they are going to function properly in the STEM world. And of course, it's also going to be useful for anybody who is trying to review basic mathematics. I am Dr. Ganguly. So first I'm going to present the 10 questions. So to get maximum advantage of the video, you can take a look at these 10 questions and then you can try to solve them. And then you can go to the later part of the video where I'm going to discuss the solution. So let's look at the questions first. So question number 1 asks you to find an integer solution of this equation 3 to the power x equals x to the power 9. So the fact that you have been told that the integer solution has to be found makes your life somewhat simpler. Question number 2 asks you to find the Laplace transform of this function. Now, Laplace transforms are extremely important in different fields. For example, if you are doing anything in control systems, also in solving differential equations, particularly electrical engineers love Laplace transforms. So very often different integration questions which you may be asked are actually couched in terms of Laplace transform. So that's what we do here also. Question number 3 asks you to find the area of a circle of radius r by using the equation of a circle and by also using integration. So of course you know this is going to be pi r square, but you are asked to derive this. Question number 4 asks you to find out this integral, that is the integral of log x dx. Question number 5 wants that you should show that sine x is approximately equal to x minus x cubed by 6 when angles are small, that is x is a small angle. So many a time we use the fact that sine x is approximately equal to x in various calculations where we are trying to get rid of complexity, but actually it's a series, so that's a hint there. You can figure out what is this expansion and then try to get this particular equation. Now question number 6 asks you to find the sum of this following series, which is essentially the sum of the first 100 integers. Question 7 asks you to find the sum of this following series, which is 1, 2, 4, 8, 16, 32, and so on. So of course you can see that what's happening in the series is that the numbers are doubling as they go along. So 2 and then you go to 4, so it's doubled, 4 is doubled to 8, 8 is doubled to 16, and so on. Question number 8 asks that you solve this differential equation, that is the second derivative of x with respect to t minus 4x equal to 0. Question number 9 gives you a particular matrix 2x 3 1, and this matrix has eigenvalues 5 and minus 2, and you have to find the values of x. Now eigenvalues are something which occur all the time in engineering, physics, and sciences, so that's a concept which people often try to test during interviews. And finally, question number 10 asks you to find the minimum point of this function. So this is a multivariate function or a function of more than one variable. So this is a pretty simple function here and you have to find the minimum point. So now what you can do is, if you are interested, you can try to solve these particular questions and then come back to the solution, which we are going to discuss now in the second half of this video. So let's start with problem number 1. So again, I have given the problem in red here, I have solved it in blue, and I have given the answer in green. So let's look at this problem here. Now, the immediate thing which will come to your mind is that why not take log on both sides? And that's something which is very appropriate to do whenever you encounter a problem where something is raised to a power which is difficult to figure out. So here of course this becomes x log 3 is 9 log x, and I can immediately write this in the form log x by x is log 3 by 9. Now, I also know that the solution has to be an integer here. So x is an integer. So there is going to be some particular combination of these numbers 3 and 9 which is going to be such that it's going to be in the form log x by x. So let's try to check that out. So what I'm going to do, I'm going to take this log 3 by 9 and multiply the numerator and denominator by 2. And so if I do that, I get here log 9 and denominator is 18. Remember that here what I can do is it becomes log 3 square. So that's how I get log 9 here. Now this is not of course in the form log x by x, but it's better than 3 by 9 because we are getting to 9 by 18. Now we take this again and multiply it by 3, the numerator and the denominator. And in this case I get log 27 by 27 because remember 3 cube is 27 and also 3 into 9 is 27. So again I can write this equation here. And of course, you observe this equation, you clearly see that this is going to be true when x is equal to 27. So that's our integer solution for this problem. Now, this problem does have a different solution also that we are going to discuss in a later tutorial that can be done by using the Lambert W function. But that's something we are going to discuss in a later video. Now let's come to problem number 2 where we were asked to find the Laplace transform of e to the power at. Now the first thing you need to remember is the definition of the Laplace transform which I have put in purple. So I'm going to put things which you should put in your memory in purple. So f of s is 0 to infinity e to the power minus st ft dt. So that's the Laplace transform of a function f of t, and typically it is written in the form capital F of s. So what the Laplace transform does is that it lets you go from the time domain, which is here f of t, to the frequency domain, which is this capital F of s. So now I put this here EAT, and then essentially it becomes a, or rather an integration problem. Now I can straight away write it in this form here, e to the power minus s minus at dt, and I can integrate this function to get this function here. Now, of course, what you have to do now is you have to substitute infinity for t and you have to substitute 0 for t, and so you get this here. So remember, when you put e to the power minus infinity, that is going to be 1 divided by infinity, and so that's going to be 0 here with the negative sign. And the second term is going to come by putting t equal to 0, so that's going to give you simply 1 by s minus a, which is this term here. So you need to take care about these signs here. So as long as you keep these signs in proper condition, you are going to land up with 1 by s minus a. So the Laplace transform of e to the power at is 1 by s minus a. Sometimes it's written in this form, so you use a calligraphic L here for Laplace, and then when you use it on e to the power at, you get this value 1 by s minus a. So here L can be looked at as an operator. Now that's something which is very interesting. Many people actually are going to test out your integration capability through using Laplace transform. So you can immediately see that if I had ft is sine t or something like that, you can easily test out people's capability in terms of integration by parts, definite integration, and so on. So many a time what engineering professors and teachers try to do is they try to couch the integration problems as Laplace transform problems, and that's why you need to always review your integration capability before any particular test. Let's come to question number 3 where we were told that we need to find the area of the circle, and of course you know from coordinate geometry that if you have coordinates x and y, then a circle is given by x square plus y square is r square, and you have to find the area within this circle. Now if we look at a small strip here of length dx, then we can say that whatever the area of this strip, we have to integrate it from x is 0 to x is r, and this rectangle is going to be y into dx. That's going to be the shaded region here. So that's what I've done, y into dx 0 to r, and there are four such regions here, so I'm going to put a 4 here. So this is a quarter of this circle. So this is actually the formula I can get. So this is like essentially a mathematical model, and this part involves converting the actual problem into a math problem. Now of course I can immediately then put y is root r square minus x square from the definition of the circle itself, where the circle has radius of capital R. And you know from these kind of integrals that the way to solve it would be to put r as, or put x as r sine t, because that's going to simplify this, because you know the fact that 1 minus cos square t is sine square t, and so on. So let's make that substitution. X is r sine t, so we get dx is r cos t dt. And so from this I can also see that when the bound x is 0 is there, that's going to give me t is 0, because if I put x is 0 here, sine t would be 0 and t would be 0. And the second case would be where x is capital R, t would be pi by 2. So again, let's put x is capital R here. So you get sine t is 1 and sine t is 1 at pi by 2 or 90 degrees. So with that I can change the integral bound. So a becomes 4 times integral 0 to pi by 2 root of r square minus r square sine square t into r cos t dt. So that was dx here. Now what I can do is I can take the r out from here. I take another r out from here. So I get 4 r square outside this integral, and inside this I simply get cos square t, because 1 minus sine square t is cos t, or rather root of 1 minus sine square t is cos t, and there is another cos t here. So that gives me this expression. Now to integrate this expression, I think we have done a problem similar to this previously. We can use the formula that cos square t can be written as 1 plus cos 2t by 2, and then integration gives me this equation here. So I cut this 2 out here, I get 2r square, and integrating this 1 becomes t, and this cos 2t becomes sin 2t by 2, and the levels are 0 to pi by 2. Now I make this substitution. When I make pi by 2, I of course get the term 2r square into pi by 2. When I put pi by 2 here, sine 2 into pi by 2 is sine pi, so that is simply 0. And also if I put t is 0 and t is 0 here, the second term corresponding to t simply becomes 0. So I have 2r square into pi by 2. Some cancellation of 2 happens here, and I get pi r square, which is the result we know from basic high school, and even before that in most cases. That's how you actually know what is pi. So now let's look at question number 5, which was integral of log x. Now this is a very interesting problem, because many people are actually completely befuddled when they see this problem, and they try to do various things. But the trick here is actually to realize that this is something which will become much easier if we could differentiate it. So of course you know that log x derivative is simply 1 by x. So if we think that log x is actually multiplied by something like 1, which of course is always present, then I can use integration by part here. So the integration by part formula is you take the first function into the integral of the second function minus integral of differential coefficient of first function into integral of second function into dx. So this immediately then gives me log x into x minus x, because these two x cancel out. So I simply have to integrate dx. I get minus x plus c. A very simple problem, but this is a problem where actually you need to use integration by parts to get the answer, and you introduce this variable as 1. So this is very interesting problem, which I find many students are not able to do if they have not seen this problem before. Let's come to question number 5, which was how can we express sine x in this form, x minus x cubed by 6, where x is relatively small. Now you will of course realize that this is coming from a series expansion of sine x, and the simplest expansion you can get is the Taylor series when you expand it at x is 0 or about x is 0. So what happens is that then you get something known as the Maclaurin series, and again I have put it in purple. This is something you should commit to your memory. So we can write the function f of x as f of 0 plus f plus x f dash 0 plus x squared by factorial 2 f double dash 0 plus x cubed by factorial 3 f triple dash 0 plus dot 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 and so on. Now what I can do is that we can take this function, that is sine of x, and we can find its value at 0, we can find the value of f dash at 0, we can find the value of f double dash at 0 and f triple dash at 0 and so on. But I think by the time we get to f triple dash, we will get the x cube term. So that's what we are interested in. So let's do that. So you know that fx is sine x, so f0 is 0, f dash x is cos x, so f dash 0 is 1, because when you put 0 value here, you know cos 0 is 1. Now f double dash x is minus sine x. Again, we know that sine x is 0 at x is 0. And then f triple dash x again reverts to minus cos x. And this, of course, we know is going to be minus 1. So when x is 0, cos x is 1. So this f triple dash x is minus 1. Then all I need to do is substitute these values here. So I can write sine x is f0, which was 0 here, then x into f dash 0, that is x into 1. Then I have the next term, x squared by factorial 2 into f double dash 0, which would be 0. And then I have the final term plus x cubed by factorial 3 from here into f triple dash 0, which was minus 1, and that immediately reduces to sine x approximately equal to x minus x cubed by 6. So this is a very important test about whether a student knows Taylor series and Maclaurin series, because if you see many subjects such as optimization and so on, they are often based on the Taylor series expansion as one of the fundamental concepts, because most problems have to be handled in a local sense, and locally most functions can be expressed in terms of Taylor series. Question number 6, again a favorite of many people as far as interviews are concerned, is simply to find the sum of the first 100 integers. And there is a very elegant solution here due to Gauss, that he was asked this question in his school and he essentially did it very quickly. In those days, probably in Germany, they wanted people to work very hard and actually try to add these numbers and see if they could diligently get it to be correct. Now, most people would probably get it wrong because it's actually very hard to sum so many numbers for a human being. It may be easy for a calculator or rather a program or for somebody to do this in Excel spreadsheet. So what Gauss did is that he simply flipped this and wrote this S as 100 plus 99 plus 98 plus 97 all the way to 1, and you simply then add these two series, so you get 2s is 101 plus 101 plus 101 all the way, because you can immediately see that each of these, when you total 1 plus 100 you get 101, you total 2 plus 99 you get 101, you total 3 plus 98 you get 101, and so on. And so immediately you can write 2s is 100 into 101, because there are 100 of these values of 101, and then after doing some simple manipulations, you can get the sum to be 50-50. Now, of course, there is a group of people who are going to answer this question by using the formula which they may already know. And in case they do that, what you are going to do is you are going to ask them to derive this formula, and that is going to lead them to this particular solution. So if they are able to do that, it's good. If they are not able to do that, that's not a good sign, because that means they only know the formula, they do not know how to obtain the formula. So you can see here S is expressed in this manner, 1 plus 2 plus 3 all the way to capital N, and again S is n minus 1, n minus 2, n minus 3 all the way to 1. So we have simply flipped this as here and got this second series. Now I add these two series, I get a whole bunch of n plus 1 here. Typically I get n plus 1 terms, so I get this here, 2s is n into n plus 1, and so I get s is n plus 1 by 2. So this, of course, is the derivation which follows the way Gauss solved this problem. Now, there are some people who may actually solve this problem by induction, and that is also legitimate, though I kind of find it a little bit troubling, because as far as induction is concerned, it can prove a particular formula, but it doesn't give you insight about how to come up with the formula. But let's try the induction method just to know what it is. So essentially the formula is given by Sn is n into n plus 1 by 2. So if I take S1, I put n is 1 here, I get 1 into 2 by 2, which gives me 1. So that of course is true, because if I only had one term, the sum would be 1. If I took two terms, I get 2, 2 plus 1 by 2, which is 2 into 3 by 2, which is 3, which of course is 1 plus 2. That is also correct. So essentially I verified this formula for the case n is 1 and n is 2. Now what I do is I try to see what is the value of Sn plus 1, and that's going to be Sn plus n plus 1 here, because n plus 1 is the value of the n plus 1th term of this particular series. So I can write Sn from this formula, I add n plus 1, and so I get this equation here. So what I've taken is I've taken 2 in the denominator, this term is n into n plus 1, and this term has become 2 into n plus 1. Now I immediately see that I can write this as n plus 1 n plus 2 by 2, because this can be easily factorized. N plus 1 can be taken out and the other term becomes n plus 2. So essentially this Sn plus 1 formula exactly has the same form as Sn. So I have proved that if S1 is true, S2 is true, and Sn is true, then Sn plus 1 is also true. So by induction we have proved this to be correct. So again, this is an acceptable answer also for this kind of problem. Now, there is a way to actually simply extend this question to get the arithmetic progression also as a question in many cases. So sometime if you are dealing with a more precocious student, you can ask them to derive the arithmetic progression formula. And again, to do that, what you can do is you can write S in this manner. So it's u1 plus u1 plus t plus u1 plus 2d all the way u1 plus n minus 2d, u1 plus n minus 1d, and then the same series flipped. So essentially u1 is taken as the last term and this term becomes the first term. Now here of course remember u1 is the first term of the arithmetic progression, un is the last term, and d is the difference between any two terms. So whenever the difference is such that any two terms, if you subtract them, you get the same value d, then you have an arithmetic progression, which is the case in this problem, because see 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1. So this is essentially an AP with common difference 1. So what I can do is I can add these two here, and so I get immediately 2s is n times this value. So if you look at each of these values, you will see that if you add them, you get a 2u1 term and a n minus 1d term. If you add this with this, you again get a 2u1 term and a n minus 1d term, because this n minus 2d plus d becomes n minus 1 into d. So this is the formula here, and I can then easily write S is n by 2, 2u1 plus n minus 1d. This is a general formula, or you can write it as simply n by 2 u1 plus un, where un is the nth term. So this again formula is in purple is something you can commit to your memory, because this is going to tell you about the arithmetic progression. So let us now go back to this series, and if we go back to the series, we see immediately that there are 100 terms here. So n is going to be this, and then this is n by 2, 2 into u1. u1 is of course 1, the first term, and then you are going to have 100 minus 1 here, and then you are going to have d, common difference d, remember, was 1 here, 3 minus 2 was 1, 4 minus 3 was 1, and so on. And so if I simplify this, here I get 99, here I get 2, so it's 101. So 50 into 101, which gives me 50, 50, which was the same thing I did previously. Now you can also use the second formula here to get this answer. So that would be n by 2, 1 plus the nth term, which is also in this case is 100, and so that gives me the same answer here. So this is something which is very important. Many a time when you are doing convergence studies or numerical convergence, you may get the values to come out in something which can be either an arithmetic progression or it could be a geometric progression. So question number 7, that actually tests your knowledge of geometric progression. So again, there is a very simple way to do it without knowing too much about geometric progressions. So we are asked to sum this series. Now Of course, you could theoretically try to add all these numbers, but a better way to do it would be simply to write this as S. And then you can realize that this kind of series has a common factor here or a common ratio. So you can see that 4 by 2 is going to be 2, 16 by 8 is going to be 2, 32 by 16 is going to be 2. So essentially 2 is the common ratio here. So I can multiply this S by 2. I get this equation here. Now I can see that there is a lot of similarity between these two equations, and so I try to subtract these two. So S minus 2S gives me 1 minus 256. All the other terms cancel out. So you see 2 2 cancels out, 4 4 cancels out, 8 8 cancels out, and so on all the way to 128 to 128. Only terms which survive are 1 and 256, and that comes here. And so immediately I can write here minus x is minus 255 or s is 255. So that's the sum of this series. Now, of course, we see that this is a geometric progression. Now, geometric progressions are also something which are very important, and you can also ask a question on deriving the geometric progression at any point, and some people may actually use the formula for the geometric progression which is given here, in which case you can ask them to derive this formula. So S is given by this expansion here, where again U1 is the first term, R is the ratio here, and it goes on like this. So U1R square all the way. And we actually flip this, we can write this here. Now what we can do is we can write RS. So remember R is the ratio here. So we multiply this S expression by R, we get this here. So what I'm doing, I'm generalizing the way I did the problem in the previous slide. So once I do that, I can subtract S from RS. So S minus RS is going to give me this term, because again all the terms are going to cancel except U1 and U1Rn. So I'm going to get this here, and so this is immediately going to give me the solution in this form, that S is U1 1 minus Rn by 1 minus R. So essentially you can find the sum of the geometric progression by knowing this common ratio R and by knowing the first term U1. Of course, this is not valid when R is 1, because in that case there is a singularity because the denominator becomes 0. So let's apply this formula to the series I showed before. This series was of the form 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 all the way 2 to the power 7. So if I substitute it in this formula, I got this value here. So I can immediately get 255 after some manipulation. So remember, U1 is 1, that's the first term here, and also remember R, the common ratio is 2 here, because 4 by 2, 8 by 4, 16 by 8, they are all 2, so that's 2 here. And also remember N is 8, because I am looking at the term involving 8, so that's something to keep in mind here. So this of course lets you calculate the problem very simply. Now of course, how did I get n is 8? Remember the typical series here, you have n minus 1 here. Okay, so that means n minus 1 is 7, so therefore n equals 8. Now we did a lot of intense math in the previous two slides, so let us cool down slightly. Let's look at this very simple differential equation which you may be asked every now and then. Now these kind of differential equations are very important. They are constant coefficient differential equation. You cannot solve them by simply integrating them or separating variables and so on, because they involve second derivative terms. So in these equations you can very easily assume that the solution has the form e to the power st, and you can see that if you take the first derivative dx by dt, you get sest. You take the second derivative, you get s square est, and you substitute this here, so you get this equation here. Now I can simplify this equation here, and I immediately realize that est is not going to be 0. The exponential function is never 0. So s square minus 4 is going to be 0. So this is known as the characteristic equation. So I get s is plus minus 2. So there are essentially two solutions here, and I can add them with two constants. So I can write x is a e to the power 2t plus b e to the power minus 2t. So this is an equation, or this type of equation come very frequently in many mathematical physics problems in many simple models such as even spring mass systems, spring mass damper systems, and so on. And so this is something you need to know. Now, this differential equation has a second order derivative here. So you end up with two constants which you need to find from something known as the initial condition. So initial conditions happen and you need to be specified the value of x at some point. So maybe you can be specified the value of x at 0 and also value maybe of x dot at 0. So these are sometimes known as the initial conditions. Now let's come to question number 9, and question number 9 involved this particular matrix. The eigenvalues of this matrix are given. So what we do is that we immediately turn to the eigenvalue problem. So if you have a 2 by 2 matrix, the eigenvalues can be obtained by setting this determinant to 0. So we take the term here and we subtract lambda, we take the term here, we subtract lambda, and then we expand this out. We again get something known as a characteristic equation. Now using the formula for quadratics, I can very easily write the equation in this form. I can simplify it to this form. Now looking carefully at this form, you will of course see that the positive root will correspond to 5, the negative root is likely to correspond to -2. So let's check that out. Let's take the positive root, put it equal to 5. So if I simplify it further, I get 1 plus 2, 12x equals 49. I get x equal to 4. Now let's see if this satisfies the second part. I can put this solution here and I get the second eigenvalue, which is the one involving the negative value here, is -2. So this is satisfied. So this again is a very simple problem which tells you about how to get the eigenvalue of a matrix or a matrix. Now many a time it happens that you may have the eigenvalues of a problem and you may actually have to find the system. That is sometimes known as an inverse problem. So most people, what they try to do is, given a matrix, they try to find the eigenvalues. Maybe the eigenvalues involve natural frequency of a system or some physical parameter, that is known as a forward problem. And when you are given, for example, the eigenvalues and you have to find some aspect of the system, maybe the stiffness, maybe the mass of a particular spring mass system, then you get what is known as the inverse problem, which are very important problems in physics. Finally, let's turn to question number 10, which involved this particular function of two variables. So we are asked to find the minimum point. Now what you can do is find the partial derivatives of this function with respect to x and y. Now to find the partial derivative with respect to x, you treat y as a constant in this equation. So if I do that, I will simply get 2x minus 2 because y is a constant, and therefore only x square and minus 2x terms have to be differentiated. Now if I want to find df by dy, I will get 2y plus 4 here, because when I find the partial derivative with respect to y, I can think of x as being a constant. So that's a very simple concept you can easily figure out. Now what will happen is that when you have a minimum point or a stationary point, then these derivatives are going to be 0. So that's why I have set these to 0 and I immediately get x is 1 and y is -2 as the stationary point, the critical point of this function. Now this set of derivatives, or rather I should say the value c, which is a column vector, the first term is df by dx, the second term is df by dy. This is sometimes known as a gradient vector for this particular multivariate function. That's a very important concept in optimization. I'm going to leave some links to optimization and some other important concepts such as Taylor series at the end of this video. Now this of course tells me this is a stationary point, but it doesn't tell me whether it's a minimum or maximum. To find that, you have to calculate what is known as the Hessian matrix. And the Hessian matrix typically involves second order partial derivatives here. So I need to calculate second derivative of f with respect to x square, which you clearly see is simply going to be 2. So I have 2 here. Second derivative of f with respect to x and y is going to be 0 because there's no y here. So if I were to differentiate this with respect to y, I would simply get 0. This also would be 0 here, and second derivative of f with respect to y again would be 2. So I get 2 here. Now you know the eigenvalues of this matrix are simply 2 and 2. These are the eigenvalues of a diagonal matrix. But if you want to calculate it using determinants, you can do that and you will get the eigenvalues to be 2 and 2. Now what happens is that there is a concept known as positive definiteness. And this Hessian matrix is positive definite because it has only got positive eigenvalues. Therefore, in that condition, the particular point we got 1 and minus 2 is a minimum point as far as this function is concerned. Now, some of these things such as the Hessian and all are very important in optimization. I'm going to leave some links in my final end screen to videos which are going to give you more information on that. And these concepts are extremely important in many multivariate problems, in many function minimization problems, and so on. So that was the question bank 4. I hope it helped you improve your mathematics, and certainly it will provide teachers and researchers and research managers with a bank of questions which they can use to test various students out there or various job applicants out there or PhD students. And also if you are a student of mathematics or a student in general in any STEM discipline, it's going to help you improve your math knowledge and also become a better person as you learn more and more mathematics. So I will end my video here and make sure you look at the videos on the end screen to delve further into some of the concepts we have touched upon today. And if you have not read the or seen the previous question banks, make sure that you go through them in your free time, maybe during the weekends, and try to understand the different problems and their solutions.